Hello everyone. In this video we're going to talk about aldehydes and ketones. Specifically, we'll learn how to name them and talk about their physical properties. Recall that an aldehyde and ketone are functional groups that contain the C-double bond O, which is a carbonyl group. The aldehyde has at least one hydrogen bonded to the carbonyl carbon. Ketone has only carbons attached. The ketone group, the carbonyl group I should say, has a moderately high polarity. Realizing this will help you to understand many of its important physical properties and the way that it behaves chemically. In naming aldehydes and ketones, two systems are used, a common naming system and the IUPAC. First, let's look at the common names. Here are a couple of examples. This compound has the common name formaldehyde. And I think you're familiar with formaldehyde. The aqueous solutions are called formalin. It's a biological preservative. This is acetaldehyde. All right, ketones. This is the most important ketones used as an organic solvent. It has the common name acetone. Now, an optional way to name ketones is this. One simply names the two carbon groups attached to the carbonyl group, and those groups are named in alphabetical order using separate words for them. So this particular ketone, the common name is ethyl methyl ketone. Ethyl alphabetically coming before methyl, so it appears first in the name. All right, this one, the two groups are, this is the phenyl group, and the benzene ring is a substituent, we call it phenyl, and this group here is isopropyl. Isopropyl alphabetically comes before phenyl, so the name is isopropyl phenyl ketone. All right, naming aldehydes and ketones by the IUPAC rules. Let's first look at aldehydes. What you do is count the number of carbons in the longest unbranched chain that contain the carbonyl group. And then as a starting name, you write the name of the corresponding alkane having the same total number of carbons. So in this case, there's 1, 2, 3, 4, 5 carbons, the unbranched chain. The starting name will be the continuous chain alkane pentane. All right, so we changed pentane so that it is named as an aldehyde. We do that as follows. We drop the E ending here and add the suffix al, and it becomes pentanal. If you're writing this name cursively, be careful. Some people's A look like O's. And for example, if this A, the end looked like an O, it'd be pentanol, and that's an alcohol. All right, if you have substituents present, what one does is you number the carbons of the longest unbranched chain, that's called the parent chain. Carbon number 1 is the aldehyde carbon, and then go ahead and number the carbons down the chain. So in this particular example, this is carbon 1, and 2, 3, and so forth. Then look and see what substituents are attached. The substituents are named. If they're different, they're named in alphabetical order. If you have 2 or more like substituents, then you use numerical prefix di, tri, and so forth. And you indicate the name of the substituent and the location number. Here we have the ethyl substituent. It's on carbon 3, and you have two methyl substituents that are attached to carbon 5. Now, alphabetically, ethyl comes first, so we'll name it first. So we're going to say, for the name 3-ethyl, 5,5-dimethylhexanal. It might seem to be redundant to repeat the 5, but that's consistent with the important rule that every substituent has to have a location number, even if that number gets repeated. All right, naming ketones. Look at this example. Count the number of carbons in the longest carbon chain containing the ketone group. The starting name will be the name of the unbranched chain alkane. This is a 1, 2, 3, 4, 5, 6, 7. Okay, that's supposed to be a starting name heptane. I wrote hexane. It's a little error here. What you're going to do is so that it's the name of a ketone, you drop the E and add the suffix one, and now here it is correct. This becomes heptanone. Heptanone. Well, a heptanone ketone can have the carbonyl group in any number of different positions. So we have to indicate in the name where that ketone group is located, and here's the rule. You number the carbons of the chain that's nearer the ketone group. So here we would go from the left 1, 2, 3, 4, and so forth. The carbonyl group, the ketone group is at number 2. So we'll take that number 2 and put it in front of the parent chain name 2-heptanone. 2-heptanone. All right, if substituents are present on the parent chain of a ketone, we'll proceed just as we did with aldehydes. You're going to provide a prefix name for each of the substituents. They're going to be named in alphabetical order, and a location number must accompany each substituent. In this example, well, let's first count the number of carbons. That's a 1, 2, 3, 4, 5, 6, 7. Heptane's a starting name. Change that to heptanone. All right, now we need to number the carbons from the end near the ketone group to establish the location number. So we'll number from the right end rather than the left and go 1, 2, 3, 4, 5, 6, 7. We have an ethyl substituent and a chlorine or a chloro substituent. Of the two, chloro substituent alphabetically comes first, so it's named first. With its location number, you would say 5-chloro, and then 4-ethyl, 3-heptanone. All right, hope that's clear. All right, ketones can be a part of a ring. They're called cyclic ketones. How do you name them? Well, this example, start out with the name corresponding to the cycloalkane. A 5-carbon cycloalkane is cyclopentane. Drop the E and add one, you have cyclopentanone. In this example, that's a 6-carbon ring, and would become then cyclohexanone. We have on the cyclohexanone a propyl substituent. Now, we have to indicate where it's located. The rules for numbering the carbons of the ring are this. It is named as a ketone, so the ketone group has nomenclature priority. Carbon number 1 is the carbonyl carbon. You then number the carbons in the ring in the direction that assigns the lower number to the first encountered substituent. So we want to go to the right 1, 2, 3. So our propyl substituent is on carbon 3. So the name for this compound is 3-propyl cyclohexanone. Okay. Now, we've learned, I should say you have learned, hopefully, how to name a number of different functional groups, alcohols, aldehydes, ketones, haloalkanes, and so forth. you can understand that you could have a compound that, let's say, has 2 functional groups in it. Well, the issue then becomes, how would you name that compound? Let's look at an example of this one here. This has 2 functional groups, the ketone group and the alkene group. The question is, should you name it as an alkene with a ketone in it, or should you name it as a ketone with a alkene in it? Well, in IUPAC rules, functional groups like this have a nomenclature priority. Groups that have a higher oxidation number are given higher priority. That means things that have groups with larger electronegativities or larger number of atoms with high electronegativities are given higher priority. So the carbonyl group has oxygen in it. The C double bond C has only carbons. Oxygen has a higher electronegativity than the double bond carbon. So the ketone group has nomenclature priority. So this is going to be named as a ketone. That means it has ONE at the end of the name. So what we want to now do then is count the number of carbons in the ketone chain. That's 1, 2, 3, 4, 5, and a starting name would be pentanone, assuming a single bond here, and we will now have to change that to pentenone because there's a double bond in the parent chain. So this is basically a pentenone as the parent chain. Now, what we're going to do then, since the ketone has higher priority, we number the carbons from the end that's near the ketone group and go 1, 2, 3, 4, 5. All right, so we want the, we have to indicate now the location number of each functional group. The ketone, which is the main group, and then the location of the alkene group, which would have a lower status, functional group status. And so what we want to do is put the location number as close to the group it refers to as possible. And so here we go. We know this is a pentenone. The ketone's at position 2, so we'll write the number 2 just in front of the suffix -one, pentene-2-one. The location of the alkene group. Alkene carbons between 4 and 5. Remember, when we're naming alkenes, we use the lower of those 2 numbers. So we're going to say 4-pentene-2-one as the IUPAC name for this compound. So I hope you follow that okay. I think I have exercises where you're going to be asked to name a compound that will have like 2 or more different functional groups. Might have something with an alkyne group in it, triple carbon-carbon triple bond, and an aldehyde group in it, and so forth. Okay. Now, let's talk about some basic physical properties of aldehydes and ketones. Now, as we do this, we're going to touch on principles that we have discussed the first semester, and I think everyone understands that, and there's been references to it here and there throughout this whole course. But let's first look at boiling points of aldehydes and ketones. The boiling point reflects the strength of the attractive forces between the molecules in the liquid state. Now, the stronger the forces between the liquid molecules, between the adjacent liquid molecules, the harder they are to pull apart, the harder they are to convert liquid to the vapor form, and you would see a higher boiling point. So if the liquid in question, if the attractive forces between the liquid molecules are higher or stronger, then that liquid would tend to have a higher boiling point. This is well, we're going to look at try to predict the relative boiling points of these three compounds. These three compounds are close in their molecular weights, and I tried to make them as close as possible in terms of their structure. This is 1-propanol, this is acetone, and this is butane. We want to see which is the highest boiling, which is the lowest boiling of these three compounds. What you have to do, of course, is to determine the type of attractive force in each of those compounds. And this particular case, the alcohol, the dominant attractive force is hydrogen bonding. The OH group of one alcohol molecule can be attracted in a hydrogen bond way to a second alcohol molecule. Now there's also van der Waals or dispersion forces present because of the three-carbon chain here, three-carbon alkyl chain. And so there is, to some degree, dispersion forces, but that's true of almost any organic compound. If you ask what the type of attractive forces are for a compound, you can almost always say, well, to some degree, dispersion or van der Waals is going to be there because that compound will have carbons in it, which tend to be nonpolar and are subject to that type of attractive force. Well, for the alcohol, the dominant one is hydrogen bonding. Hydrogen bonding, recall, is of the three is the strongest. The acetone molecule, remember we mentioned the carbonyl group is a moderately high polarity. The ketones can't hydrogen bond with each other, so the type of attractive force present in the ketone would be dipole-dipole. The acetone molecules are polar, so two adjacent polar acetones would be attracted, opposite charges attracting. Butane here is essentially a nonpolar compound. The type of attractive force working for it is what we call dispersion or van der Waals. And the two butane molecules come close together as they would in a liquid. They're going to polarize each other. Adjacent molecules are going to polarize each other. At any given time, there's going to be a polarization and there's attraction between the opposite and negative charges, and that's what holds them together. Now, the magnitude and the direction of those electrostatic forces will change with time, but at any given time, there's some kind of attraction, and that's what holds them together. Of these three, the strongest is the hydrogen bonding, and the weakest for equal size shaped molecules is the dispersion. Okay, now, so to see which of these is the highest, which is the lowest, the alcohol with the hydrogen bonding, that should be the highest because hydrogen bonding is the strongest of the three types of attractive forces. Dispersion is the weakest of the three, therefore the butane should have the lowest boiling point. And indeed, these are the observed boiling points, the normal boiling points for these compounds. The highest boiling one is propanol, as predicted, 97 degrees. Butane here is the lowest, around 0 degrees Celsius. Acetone is in the middle, literature boiling point of 56 degrees Celsius. All right, now I want to talk about some principles with respect to solubility in water. Now we know a bit already about principles of solubility. I've referred to and used this little chestnut that says that like dissolves like, and that rule, empirical rule, is okay. It'll get you pretty far through the circumstances that you'll encounter with respect to solubility. But I'm going to show you a little bit different wording of that principle, which is more, I think, more principle-based. And, well, let me explain what it is. Okay, so solute will tend to be more soluble or less soluble in a solvent, excuse me. The solute will tend to be more soluble in the solvent if there's a relatively stronger attraction between the solute and the solvent. If there is a weak attraction, relatively speaking, between the solute and the solvent, then it will tend to be not so soluble. Now, for organic compounds, what will determine the strength of the attraction between that compound as a solute and water is the presence of functional groups that can hydrogen bond with the water solvent. And if a compound has a functional group that can hydrogen bond to water, then that represents a strong attraction to water, and that would be a strong force in favor of that substance, of that solute, being soluble in water. If a compound has only carbons, that is, as we know, insoluble in water. There's no hydrogen bonding force or even a polar force that's going to attract it to water molecules. The only thing working for it is a very weak van der Waals attraction between that and water. So what we find here is this, that the issue is the solute in question, the organic solute, the number of carbons and the number of hydrogen bonding groups in the molecule. The larger the number of carbons and the fewer the hydrogen bonding groups, then that solute will tend to be less soluble in water. On the other hand, if a compound has more hydrogen bonding groups and fewer carbons, that compound will tend to be more soluble in water. The kind of cutoff point here is like 5 carbons. If you have a 5-carbon organic molecule with a hydrogen bonding group present, that is the largest number of carbons you could have and still have that compound be soluble in water. If there's more than 5 carbons, then that solute would tend to be not soluble in water. If there's fewer than 5 carbons, it would, of course, tend to dissolve in water. So whether a compound is soluble in water or not, whether there's going to be a relatively strong attraction between the solute and the solvent water, depends on the ratio of the number of carbons and the number of hydrogen bonding groups. Now, I have developed here what I call the solubility ratio rule. It's an empirical rule that probably, if you apply it, probably has a lot of cases where it breaks down. It's not a perfect rule, but more times than not, I'm going to say is that it'll give you a pretty good handle on predicting water solubility. And SR is the abbreviation for solubility ratio. What one does is, there's a little formula here. You calculate the solubility ratio value, which is defined as follows. It's a total number of carbons in the molecule. Just count up all the carbons, including the carbons that are part of any hydrogen bonding group. Divide that by the total number of hydrogen bonding groups, and you get a number. If the value is less than or equal to 5, the organic compound we predict to be water soluble. If the solubility ratio value is greater than 5, we predict that compound to be water insoluble. And I'll show you some examples in the next slide. Right here we just mentioned some examples of groups that can hydrogen bond attract to water. Alcohol group would be expected to hydrogen bond with water, either donating hydrogen or accepting a hydrogen from water on the oxygen. Ketone or aldehyde group or an ester group would also be able to hydrogen bond to a water molecule. An ether group itself can accept a hydrogen bond from water on the oxygen. The carboxyl group is also a group that can hydrogen bond to water. Now it has a carbonyl group and an OH. There are actually two functional groups. You might think that it might count as that we double count it, but experience shows that the carboxyl group behaves just as a single hydrogen bonding group, and so if we have a carboxylic acid in a molecule, we'll count it as just one hydrogen bonding functional group. And I'll mention here that in this rule I've not included aliphatic amines. Those are the nitrogen-containing compounds because they tend to be more soluble than the oxygen-containing compounds, and the solubility ratio rule that would probably work better is if the SR value is less than or greater than 6, it's likely that it would be soluble in water. But don't take this rule to the bank because I haven't really tested it out yet. All right. There's a cautionary note here, though. Implicitly, the compounds we're talking about here are electrically neutral organic compounds. But an organic compound can also be ionic. That's what we call a salt, specifically an organic salt. A salt has a cation and an anion. If either the cation or the anion or both are organic, we refer to that as an organic salt. The overriding exception here to the solubility ratio rule is this, that if you have an organic salt, do not apply the solubility ratio rule at all. Because in general, organic salts tend to be water soluble regardless of the number of carbons that are present, regardless of the calculated value of SR. So, all right. With that in mind, let's look at the next slide, at these examples. So we have this ketone. We want to count the total number of carbons. That's 1, 2, 3, 4. The ketone counts as one hydrogen bonding group. Water molecules, the solvent can donate a hydrogen to the oxygen in a hydrogen bonding arrangement. So solubility ratio value, the total number of carbons is 4, the number of hydrogen bonding groups is 1, 4 divided by 1 is 4. 4 is less than 5, we predict this compound to be water soluble. And indeed, this is, you would find that this is water soluble. Oh, what's the name of this? I don't have it written out. 1, 2, 3, 4. Butane's our starting name. Butanone. We number the carbons 1, 2. It's 2-butanone. All right, let's look at this compound. Solubility ratio value. Total number of carbons, 6 in the ring and 1 here. That's 7. The alcohol counts as one hydrogen bonding functional group. So it's 1. 7 divided by 1 is 7. 7 greater than 5. Predicted to be water insoluble. And we look at this compound. Number of carbons, 1, 2, 3, 4, 5, 6. Solubility ratio value, 6 on the numerator. Now there are these two hydrogen bonding groups, the ketone group and the alcohol. Each counts as 1, so it's 1 plus 1 is 2. So 6 divided by 2 is 3. 3 less than 5. We predict this compound to be soluble in water. And now we come to this one. This is an organic salt. And you notice there's no SR calculation here because, consistent with my little warning here, do not apply the solubility ratio to such a compound. Simply do this. Regard it as likely to be soluble in water. Most organic salts are. All right. In the next part of the video, going to talk about synthesis and reactions of aldehydes and ketones. With respect to the synthesis, my comments will be brief. I will not introduce any new reactions for making aldehydes and ketones for a simple reason. They require chemistry that we really haven't studied yet. But let me review reactions that we have studied before, which in fact could be used to prepare an aldehyde and ketone. Hopefully you'll remember these. In the chapter on alcohol reactions, the oxidation of alcohols, the oxidation of primary alcohols with the spatial reagent PCC in methylene chloride will produce an aldehyde. if one takes a secondary alcohol and oxidizes it with one of the stronger oxidizing agents, then one will make a ketone. Remember, in the Friedel-Crafts acylation reaction, that reaction can be used to synthesize a phenyl ketone. Now, let's begin talking about the reactions of aldehydes and ketones. This is going to be a rather large topic with lots of subtopics. First thing to note is that the main reactions of aldehydes and ketones are additions to the carbonyl group. Well, note we have a double bond, C double bond O, and that calls to mind the fact that if we have a C-C double bond in alkene, remember alkenes, their primary reaction is addition, and so we have a parallel situation here. Majority of reactions of aldehydes and ketones are addition to the carbonyl group. All right. Now, in this slide, we mentioned that the addition reaction follows an overall pattern, and namely this. The carbonyl group, remember, is a polar group. The oxygen partly negative and the carbon partly positive. The vast majority of addition reactions to aldehydes and ketones are ionic. The adding reagent consists of an electrophile, nucleophile. Either they're tethered together or they're separate. And the pattern that's followed is this. The electrophile part, positive, seeks out the negative oxygen and bonds to it. The nucleophile, being negative, with, of course, an electron pair, seeks out the positively charged carbon and forms a bond to it, and the double bond breaks to a single bond. Now, that's just the general addition product that forms. The chart here is helpful in that it assists one in finding the electrophile and the nucleophile. On the electrophile side, you can see we have some representative electrophiles, hydrogen ion, metal plus. These down here we'll get to later on. Nucleophiles include a sulfur oxygen negatively charged, a hydride ion, a carbanion, a halide ion, although this is less common, cyanide ion, where generally the carbon is the nucleophilic atom, and then the N minus of an amine. And this one has a complication with it, which we'll go into detail later on. To see how we use that chart, let's look at some examples. Here we have the reaction of an aldehyde and water. Right, what will be the product? Well, the first thing when one sees this, just as one sees a C-C double bond of an alkene, think addition. Right, so you see this and one thinks, addition. And as well, there's the pattern. The idea is to find the electrophile and the nucleophile. And our chart, again, will help us. We're going to actually, for the electrophiles, kind of start from the top and work our way down. So in the case of a water molecule, you can see the way to break it up is hydrogen ion is the electrophile, H+. The remainder, OH-. That's going to be the nucleophile here. And here we have it represented, L-. So we just piece it together as we show here, and boom, we get our product. This is called the hydrate of an aldehyde. All right, here we have the reaction of a ketone and an alcohol. Again, addition is what's going to happen. Look for the electrophile first, going down the top. Well, the logical electrophile would be H+. And the nucleophile is the remainder O-. H+ attaches to the oxygen. The nucleophilic methoxide ion bonds to the carbon, double bond breaks down to single, and there you go. It has a name, it's called a hemiketal. We talked about that in more detail later on. All right, here we have cyclopentanone reacting with an organometallic. Well, remember that when we have an organometallic, the thing to do is to write it in its ionic form. And we do that, as shown here. We have metal Li plus and methyl carbanion. Well, that's broadcasting to us what the electrophile and nucleophile is. So the lithium plus is going to attach to the oxygen. The methyl carbanion nucleophile bonds to the carbon. And you can see that metal plus occurs second on the list on the electrophiles. All right, so when you piece all that together, you get this as the addition product. This is a lithium alkoxide salt. Now, if we did nothing else, this would be our final product, our final addition product. One could go through the chore of isolating that, and generally we don't. We do this. We add acid to it. It's called the acid workup. H plus protonates the oxygen, and we get our alcohol here. And I'll mention this is that, in fact, a lot of the reactions that we'll see for the remainder of the course, the product is often an organic salt. And generally speaking, we don't stop there. We don't try to isolate or purify the salt because that's hard to do and they have no real value. So we almost always do either an acid or base workup to convert that salt to a neutral compound. And that's what we're doing here, converting the lithium alkoxide salt to an alcohol. Now, I've shown you the overall pattern. We ask an important question: what is the actual mechanism of this addition process? That's what I want to discuss now. The mechanism depends on whether the conditions are basic, neutral, or acidic. If it's base neutral, it follows a mechanism. It's called nucleophile induced. If it's under acid conditions, it's going to be catalyzed actually by H plus. All right, first, under base neutral conditions. What leads the attack here is the nucleophile itself. Now there's two possibilities. A nucleophile could be negative, Nu minus, or it might be neutral, in which case there's a hydrogen attached to the nucleophile. But we'll look at this possibility just a bit. Right, step one, the negative nucleophile is attracted to the positive carbon. It will attach to that carbon, pushing the electron pair onto the oxygen. This alkoxide now, having a negatively charged oxygen, is going to be strongly attracted to the electrophile. The electrophile forms a bond to that oxygen, and that gives you your final addition product. Of these two steps, attachment of the nucleophile is the slow step. It's the energetically hardest step. Now, in this case, this is where our nucleophile is neutral. There's a little extra step that comes in. But like our first case here, the nucleophile will attach to the carbonyl carbon. That is the first step. It's a slow step. Now, what we have to do here, we'll always have a hydrogen attached to the nucleophile. When that nucleophile attaches, it'll get a positive charge. The hydrogen attached to the nucleophile will break off as a hydrogen ion. Then a second molecule of the nucleophile, remember there's a hydrogen attached, it actually plays the role of donating a hydrogen ion to the oxygen here. And that gives you your final addition product. All right. Now, in the case of under acidic conditions, this reaction turns out to be catalyzed by H plus. I think we mentioned this before, that when you have a catalytic process, it's actually three phases. Phase one, the catalyst attaches to the reactant. That's going to make the subsequent reaction of the reactant easier, because it's going to introduce a new energetically lower pathway. So the harder things are made easier by the attachment of the catalyst. And so that phase 2 occurs. And then phase 3, really two things happen. The catalyst breaks off, is regenerated, and the final product is formed. And that's going to happen right here. So under acid conditions, H plus is going to naturally attach to the oxygen. That oxygen is a weak base. And we get this protonated ketone or aldehyde. All right, the second step, the nucleophile, it'll be neutral and have a hydrogen there, is going to bond to this carbon. Now, I haven't shown it, but you can draw resonance structures where the second resonance structure would have a full plus charge on the carbon. That demonstrates that there's a strong electrostatic attraction for the nucleophile and the positive carbon. This, when that nucleophile attaches, that gives you this addition product. And all we have to do then, this is phase 3, is break a hydrogen ion off the, right here, the nucleophile. The H breaking off regenerates the hydrogen ion that was used in step 1, so that once this is broken off, it's ready to catalyze another reaction. And we have our final product formed here. Oh goodness, I just realized here now that there is a error. Oh my God. If this is on, if I had an actual whiteboard, I'd be able to immediately correct it. I don't have the tool to do that, but the NU right here should be a G prime, all right? So cross out the NU and put a G prime. Now, of these 3 steps, step 2 is actually the slow step. And if you think about it, that's the energetically harder step, attachment of the nucleophile. However, this is where the catalyst comes in. If the nucleophile tried to bond just to the neutral carbonyl group, it would be harder. But when the hydrogen ion is attached, that increases and enhances the positive charge on that carbon, facilitating the attachment of the nucleophile. That's how the H plus actually works. That's how it works as a catalyst. It makes the attachment of the nucleophile easier because there's now electrostatic attraction between a nucleophile and that carbonyl carbon. It's still an energetically harder process. It's still a slow step, but it's made easier by the presence of that H plus. All right. What I want to do is, this is going to bring us to the end of this part of the video, but I want to take a look at the reactions of aldehydes when they're reacting with an alcohol. The G, just my symbol for organic group. Now, let's go through the addition pattern, see what the product is. We're going to again apply that pattern here. So H plus is going to, from the alcohol, is going to be the electrophile, and O minus is the nucleophile. So H plus attaches to the oxygen, the O minus attaches to that carbon, and there's your addition product. Likewise for the ketone, similar thing happens here, and you get this addition product. Now, in terms of the theme of addition to aldehyde and ketone, the carbonyl group, that would be the concluding part. We could just say, we'll move on. However, I'm going to introduce a second reaction that will occur here. It will occur if you have excess alcohol and H plus present, acid present. If you don't have the H plus present and so forth, it would stop at this addition product and this. But let's, we're going to take it further, one reaction. And it's this. This second reaction that will occur under the conditions that I mentioned is a substitution reaction. The OH gets replaced by the O carbon group here. It's a substitution process. Down here you have the same thing. The OH is replaced by O carbon to give this substitution product. Water is going to be the byproduct. Now, again, this would be the natural product that would occur if you have at least a 2-to-1 mole ratio of alcohol to the aldehyde or ketone and the presence of a hydrogen ion. Now, these two addition products and these two final substitution products we give names to, and I just want to call your attention to that. The aldehyde reacting with water going all the way to this final product is called an acetal. Now, think of it in this way. The A of acetal corresponds to the A of aldehyde. Down here in the ketone, if you go all the way to this final product, this is called a ketal. Now, these are new terms, so I want you to pay attention. Think of this. The KET of ketal corresponds to the KET of ketone. Now, this addition product here, interestingly, is at the 50% point in this overall process. It's halfway between the starting aldehyde ketone and the final acetal ketal product, and guess what? We call them hemiacetal, hemiketal. Hemi, of course, it means half of, like a hemisphere is half of a sphere. So that's where the term hemiacetal comes from. Now, this next slide basically summarizes this. We're going to kind of stand back and look at the overall result. If you have an aldehyde or ketone and you mix with it alcohol in a 2-to-1 ratio with H plus present, there is an addition reaction followed by substitution to give this final product. In the case of aldehyde, the final product is acetal. In the case of a ketone, with a 2-to-1 mole ratio of alcohol present and H plus additionally present, there's an addition process followed by substitution producing the final product, the ketal. Aldehyde gives the final product acetal, ketone gives as a final product ketal. Now, in a sense, we've learned actually 4 new functional groups. These are really important, and in a later video I'm going to come back to this, but basically I want everyone to learn what the basic structure of a hemiacetal and hemiketal are, and the structure of an acetal and ketal. I don't want to go into the structural details now, but I will in an upcoming video. This is really important. All right. Now, what I want to do next is, we've already explained the mechanism of addition. The addition mechanism, well, it depends on whether there's acid present or not. If there's not acid present, it's called nucleophile induced. And if there is acid present, there's an acid catalyzed process. Now, in this overall reaction, going from aldehyde to acetal, ketone to ketal, the H plus present catalyzes both the addition and the substitution reaction for both aldehyde and ketone. And what I want to do now is to show that mechanism in detail. That's what we're going to do in this slide. So my attempt here is to do this in a general way. G stands for organic group. Z stands for hydrogen or carbon. So if Z is hydrogen, you're talking about an aldehyde. If Z is carbon, we're talking about a ketone. Whether it's aldehyde or ketone, the same basic pathway is going to be followed. All right. So this mechanism will occur when acid is present. There's going to be catalysis by H+. All right. So here's basically what happens. From the get-go, the hydrogen ion is going to bond to the hydroxyl. The carbonyl oxygen, rather. In the next reaction, this carbonyl-carbon, its positive charge is increased, which is going to additionally electrostatically attract the nucleophilic oxygen of alcohol, which is going to facilitate the alcohol nucleophilically attaching to that carbon. And it will do that, and it produces this addition product. Now, a loss of H+ from this portion here will produce the hemi species. If we start out with aldehyde, you get hemi acetal. If we start out with ketone, you get hemi ketal. Now again, as long as extra alcohol and H+ is present, here's what's going to happen. The H+ that's in the mix will now bond to the hydroxyl group of the hemi species. That converts the OH to a protonated OH. You have here basically an enhanced leaving group, the elements of water. Water being now a good leaving group because when it breaks off, it's a neutral, stable, weak base. So what's now going to happen next is this is going to eliminate water. The elimination is facilitated by the lone pair on the oxygen moving in to push off the water molecule. That's what the curved arrows are showing here. Now, when you break off the water, keep in mind this has an overall plus charge. Water is neutral. That means that the residue species here has a positive charge. It's a carbocation. But it's a carbocation that actually has resonance stabilization. The lone pair on the oxygen is pushed in and delocalized into that CO bond. Right, now this resonance stabilized cation is now going to undergo attachment by a second alcohol molecule. The oxygen from the second alcohol will nucleophilically attach to that carbon, and it gives us this species. Now we're almost there, at the completion point. All we have to do then is break off the hydrogen ion from this portion here. Ejection of the hydrogen ion occurs, and two things happen. We regenerate the acid catalyst, and we form the final product, which will be either either acetal or ketal. Just a quick comment about the difference. Remember, the acetal came from an aldehyde, so that means that if it started from an aldehyde, it's acetal. The Z here will be a hydrogen. If it started out as a ketone, where Z is carbon, the Z here will be a carbon group, and that would be then overall ketal. So I hope everyone follows this pathway okay. I'll mention that going from this point to the addition of the alcohol here that corresponds to the acid catalyzed addition of alcohol that we talked about previously, or rather I should say just the acid catalyzed addition to the aldehyde or ketone. What's new for us in this video is from the hemi-acetal or hemi-ketal, the pathway for the substitution reaction, giving the acetal or the ketal. The OH group is replaced by O carbon group. All right. Now, I want to discuss one more reaction, in chapter 20. And in terms of new reactions that I want to cover, this is going to be a kind of a completion point. We actually haven't covered enough material to start thinking about our second exam. Basically, the second exam will include chapter 18, 19, and half of chapter 20. I'm not going to do the entire chapter 20. Now, so this new reaction that I'm going to discuss is a reaction between aldehydes and ketones and amines. This is going to carry a little surprise with it. We're going to see a big difference between the amine reaction and what occurs for other compounds. I will mention then, after I finish this topic, I have one more little mini topic to go over, but that's going to be, I think, in the next video. All right. Now, before I talk about the details of the reaction of aldehydes and ketones with amines, let's kind of stand back and put things in perspective. The major reactions of aldehydes and ketones is, of course, addition to the carbonyl group. But there is kind of a secondary theme to this chapter 20. If you reflect on it, think about it, some of the addition reactions that we have reviewed, there is a follow-up, a subsequent reaction. We just saw that, after all, in the case of where alcohol adds to the aldehyde and ketone. If you have H plus present and extra alcohol, there's a subsequent substitution reaction. I don't have the diagrams to show you, but there was one other reaction where we saw the addition product undergoing a substitution reaction. This will, I think, be reviewed later. But this is a sort of sub-theme to chapter 20. The main theme, addition to the carbonyl group. The sub-theme, a subsequent reaction to addition. Now, that subsequent reaction is going to be different types of reactions. The one we just studied here is a substitution. This is going to be the case in our reaction with amines, a subsequent reaction, but it's not going to be addition, it's actually going to be elimination. So let's now take a look. Now, we have to make a distinction between primary amines and secondary amines. The chemistry is going to be different. Now, it's been a while since we've talked about amines, way back the first semester, so I want to review the difference between a primary amine and a secondary amine. All right, a primary amine has just one carbon group on the amine nitrogen. A secondary amine has two carbon groups on the amine nitrogen, though it won't be an issue if you had three carbon groups on the amine nitrogen. That's called a tertiary amine. All right. First, we're going to look at the reaction of primary amines. Then we'll look at secondary amines. Now, the good news here is that order is going to be followed with both primary and secondary amines. There is a reaction, and that reaction is, following suit, an addition reaction. And the addition reaction is going to follow the pattern we've previously described. So let's now look. This reaction I want to mention is going to be catalyzed by acid. The acid that you use, it has to be kind of a controlled pH. Talk about that in just a minute. But let's see how the addition pattern is being followed. This is the addition product. The nucleophile is nitrogen. The electrophile is H+. So H+ bonds to the oxygen of the carbonyl group. The nitrogen of the amine nucleophilically attaches to the carbonyl group. The double bond drops down to the single. Now, if nothing else happened, that would be a product, so forth. But you can note the brackets here. If you recall the interreaction pathway, when you see something in brackets, it means that it has fleeting lifetime. It's going to be a reaction intermediate. It's not going to stop at that point, but it's going to react further. And the further reaction is this. It's going to lose the elements of water here, HOH. Elimination, 1,2 elimination produces a double bond. Here it's a carbon-nitrogen double bond. And this final product is formed. This is called an imine, and that's new to us. That's a new functional group, which I, of course, want you to learn. Water, of course, is a byproduct. Now, this reaction, as they say, occurs spontaneously. There's two things. First, the addition, and then the addition product spontaneously undergoes elimination of water, dehydration, to give this compound C double bond N called an imine. Now, later I'm going to explain the mechanism of that. But I want to now look at what happens with secondary amines. All right. Well, addition pattern is going to be followed. This hydrogen on the nitrogen is an electrophile. It breaks off as H+, which is going to bond to the carbonyl oxygen. The amine nitrogen is a nucleophile that's going to bond to that carbonyl carbon. The double bond breaks down to a single bond. And this is the structure of the addition product. The square brackets tells us that this has fleeting lifetime. And as before, it's going to spontaneously undergo an elimination reaction. It's going to spontaneously undergo an elimination of water. But there's a big, big difference, though. Before, when we eliminated water with the reaction of a primary amine, the OH here came off with the only hydrogen on the nitrogen. But in the case of a secondary amine, there is no remaining hydrogen on the nitrogen, so it can't eliminate water in the same way. Well, this addition product seems to have a penchant to undergo elimination rather. It just wants, it craves to undergo elimination of water. So generally speaking, it looks on the other side of the carbonyl group. It finds, if it is present there, if there's a hydrogen covalently bonded to the next door carbon, that's called the alpha, this is called the alpha carbon, the hydrogen attached called the alpha hydrogen. This alpha hydrogen is going to eliminate with the OH that's breaking off a water molecule and leaving a double bond, not between the C and the N, but between these two carbons. And this is yet a new and different functional group for us. This is called an enamine, and I want you to learn this. Let me comment a bit on the nomenclature here. Enamine. This reminds us of this special high-energy species called enol, which is a CC double bond with a hydroxyl group attached, an OH group. Enol, double bond alcohol. This is an amine group, so the name ene for the double bond and amine follows. All right. Let's look at the mechanism of the reaction of primary and secondary amines. Oh, I'll mention that if you mixed in a tertiary amine, not a whole lot happens. So we're going to confine ourselves to reaction with primary and secondary amines only. All right. recall with primary amine, there is a spontaneous addition. The addition product loses water, shown here, to give the imine. Let's look at the mechanism. Now, I mentioned that this is an acid-catalyzed process, but one has to be very careful when one adds acid. You can't just dump in acid, because the amine, being a moderately strong base, if you add too much acid, it all gets protonated and it's not going to react. There'll be no further reaction. So what we have to do is to use an acid buffer. What works best, chemists have found that if we make an acid buffer of a pH around 4.5, that's ideal. That gives you just a high enough concentration of H+ present that it's going to result in a catalysis for the reaction, but it's not so much acid that it's going to protonate the amine and stop it from further reaction. All right, step 1. H+ from the catalyst attaches to the hydroxy group here. This is the addition product. You've got a protonated OH. You can recognize here that you've got the elements of water, water being a good leaving group, with assistance from the lone pair nitrogen swinging in. This will help to push out the water molecule. You're getting a cation here. This has a name called the iminium ion. Iminium ion. Now, right here, this can break off a hydrogen ion. The lone pair swings in. Hydrogen ion comes off. The catalyst now is regenerated, ready to catalyze another reaction. And you're forming your imine product. Now let's look at the mechanism of the reaction with secondary amines. Well, the first step in the mechanism is pretty much the same as with the primary amine. H+ from the acid catalyst, and also, by the way, that I mentioned that the same thing holds here, that you have to control the amount of acid. You have to use a buffer, acidic buffer, around a pH of 4.5. Well, H+ attaches to the hydroxyl group. You're getting your protonated OH, the elements of water. Water breaks off, lone pair swings in from the nitrogen. That's what we saw before. And we have this iminium ion here. There's no remaining hydrogens on the nitrogen, though, and it needs to stabilize itself. Well, this hydrogen over here that we referred to as the alpha hydrogen is going to break off as H+. The bonding pair here swings in, forming a CC double bond, pushing out the shared electron pair here, and pushing it onto the nitrogen as a lone pair, and boom, we have the formation of our product, the enamine.
Thank you for watching. In the next video, we'll explore additional reactions and reaction properties of aldehydes and ketones.